So, welcome everyone to Guided Study Group Week 14 of Math 140. So, this week excuse me. This week again, we're gonna work on integral, and the topic today is gonna be section 5.1. It's areas between curves. So kind of like it's the same thing. It's similar to what we've talked so far. So remember in the previous week, we have say we have a curve, and if we want to find the area under the curve, we divided it into several smaller rectangle, and we just sum them all together, and we call that limit of sum of the sum is gonna equal the integral. The integral from is going to equal the integral from a to b of from a to b. So this is a and this is b. Now, if we have kind of like expand this conception, if we have a curve, two curves actually, if we have two curves and they intersect at some points and they kind of like make up these regions, then to find the area is the same practice in the sense that the area that we have, we can divide it into much smaller rectangle, and each of them, when we sum all of these areas together, we kind of like, and as we take more and more rectangles, so make the rectangle smaller and smaller, we're gonna approach like eventually push the area. Now, it's just a little bit different from last week in the sense that here, if we have this graph, the height of the rectangle is just f itself. However, here, the height of a rectangle is going to be whatever function that's on the top minus whatever functions that's in the bottom. So the height of each of them is going to be g of x minus f of x. This is going to be the height of the rectangle. Now, when we have its line between a and b, because you can see here between a and b, f is above and g is below. But from say maybe b to c, g is above and f is below. So in those cases, then say just from a to b, the area is going to be, we take the limit of n approaching infinity of the sum from I equal 1 to the n, f of xi minus g of xi, delta x. So delta x is just the width of each of the rectangle. Now, if we take that limit of n to infinity, so take the rectangle really, really small, what we end up having is that gonna be the integral of fx minus gx. Now, in this case, fx is bigger than gx, and that is taken on the graph. Now, sometimes you're gonna have like it's hard to graph f and g out, or maybe you just don't want to graph it, or the answer is in the form of absolute value. In that case, what happens is that you don't really graph it out, so you don't actually care about what is above and what is below. So you're just gonna take the absolute value, because the absolute value, the fact that it's gonna equal itself is positive, and it's gonna equal negative of it if it's negative. But in any case, the absolute value is always positive, so it allows us to make sure that a is positive, so the area have to be positive, right? Some of the problems that you might be asked in these questions, most often you're going to be asked to find the area enclosed by a region bounded by two curves or three curves. So the step is that you find all points of A and B. So find all of the points of intersections, and you put them into the integral. Now to do that, so for those stuff, usually I would say one of the other thing I would say is to graph it out. Graph is always helpful, And in this scenarios, I also want to introduce you guys to this website. It's optional, but I think it's very helpful for 2D graphing. It's a website called desmos.com. So whenever, say, you encounter a very hard to graph functions, you can try using this one to give you kind of like a general idea of like what that graph look like, some of the points that on it, like what's the shape of it, just to give you a clear thing. Even though we learned about section 3.5 before, which allow us to do all of these, some of them might be a little bit too hard for you to do on just calculations on your own. But I would say in the exam, I don't know if you can have access to another website because you're gonna be under examity, and I don't think you can open any of that, any of the software. So this is just for the purpose of practice. And the same thing for in the case of x is a function of y. So instead of we're gonna see that, say, in the example. So first example is question 20 of section 5.1. Sketch the region enclosed by x equal y fourth and y equals square root of 2 minus x. So in this scenario, this two function. One is written in the form of x and one is written in the form of y. So for the purpose of time, I already used Desmos to plot it out for you guys. So this is what we're having. Clearly the fact that you can see there are two ways we can do this problem. First is that if you take it with respect to y, so say you want to divide it into two regions, this one and that one, to find. So there are two ways that you can find this area. So the first one is now, and then this is really easy because you can see the fact that they intersect at 1. So the area is either equal from 0 to 1. Now this one, why did I divide it to two regions? In a sense, you can see the fact that on the left, the above curve is x equal y fourth, but the below curve is the x-axis, and the second sections have the above curve be y equals square root of 2 minus x, and the below is y equal x-axis. Now I would say there are two ways to do the problem, but there was one of the thing that I want to mention here. So if we use, say, the y sections, the y say like fx minus gx, then you're gonna have from 0 to 1. So what is the function of fx here? That's the thing. So you have x equal y fourth, right? So x is bigger than 0. Then you can have y equal square root of 4. So it's gonna make the calculations a little bit annoying. So minus 0, because this curve here is y equals 0. It's the x-axis. Dx plus, now again from 1 to 2. So the above curve is square root of 2 minus x minus 0 dx. So in the first one, you can easily find the integral, but in the second one, 2 minus x might be a little bit problematic because it's under the square root. However, there's another way for you to do it, and that's going to be the way that I would approach this problem, is that I'm going to take it on the y-axis. And I would say in this, please try to practice as much as possible, like try to do each problem two ways, because as I remember, this is the main focus of math 230 and 232. If you ever have to take them separately, like 231 and 232 is equal to 230. So this is a very important thing to note as well. So here, if you take it on the y-axis, you only need to care about one region, and the equation will be much simpler. So here, you have y equals square root of 2 minus x. So y is also positive. So when you square both of them and rewrite that in the form of a function of x as a function of y, you're gonna have is equal to minus y squared. So the intersection is from 0 to 1 on the y direction. So that's going to be from 0 to 1. The above curve, if you look at it this way, the height is the blue curve, which is 2 minus y squared, minus the below one is minus y fourth dy. And clearly this one is much easier to find. So I'm going to work on that, and what we're having is that it's going to be 0 to 1. You have 2 minus 1/3 minus 1/5. 22 over 15. Yeah, that's what I have for this question. I wonder if I forgot something. Right. I think that's what we have. So generally, you're gonna first need to find the intersections, or maybe even just the first step is just draw the entire regions out and see that, okay, which dimensions you're gonna work on it. Is it the the y dimension, or is it the x dimension? And then you start to find the intersection point by putting them in the function that you need. Like, say if you decided to do on all of x, so like x as a function of y, write all of them out in the form of x, take the intersections by setting them equal to one another, and then just work on setting up the integral, which curve is above, which curve is below on that direction that you choose, and just take the integral of that. So kind of like 3-man step that we have to do. Now, a second example, sketch the region enclosed by y equal cosine x and y equal 1 minus 2x over pi. Find this area. Again, the first step I would say all the time is to try to find to draw the graph out to make for the purpose of like visualization, and it's gonna save you a lot of time and kind of like improve your accuracy as well. So the red curve is y equal cosine x, and the blue curve is y equal 1 minus 2x over pi. Now, using decimals, you can also find the intersections, but I would try to demonstrate one of the intersection here. So cosine x equal 1 minus 2x over pi. Oh yeah, by the way, because the graph is everything is put in the form of y, so I'm just going to choose to do it in the direction of y as well. So this is a hard function to solve. That's why I use decimals for this, because it allows me to find these points easier. Another way you can also do that is by plug-in. So because this is trigonometric functions and like our regular functions, most of the time you should be able to plug in some common values of pi angles to put in, say pi over 2, pi over 6, pi over 4, pi over 3, or pi. And in this case, if you plug in x equal pi over 2 or pi and then 0, then you're gonna have y equal one another. So you're gonna have these three value of x to have these the function equal, so they intersect with one another. Now you're gonna have the intersects already, so you're gonna be able to find the area. So first is from 0 to pi over 2. The above curve is cosine x minus 1 plus 2x over pi dx. Another one is whatever is above. So pi over 2 to pi. The above is 1 minus 2x over pi minus cosine x dx. Now, if you want to further do this one, you can make a not further assumption, but you should be really sure about this, is that it's symmetric against pi over 2. So one thing you can do is that you can say it's equal to twice of the first integral or twice of the second integral. It doesn't really matter because the area just double. And so now it's much easier to find what is the area, what is the integral. Sine of pi over 2 is 2, 1 minus pi over 2 plus pi over 4 and you have 0, 0, 0. So what we end up having is 1 minus pi over 4. Or you have 2 minus pi over 2, because you have 2 outside. So that's what my final answer is. And you can do it by obtaining 2 integral, or just try to make like a further assumption, like observations, and then you're gonna end up like kind of like saving a little space on the calculations. But yeah, that's the case. So for the next example, it's gonna be where we're actually gonna go do graphing. So in this case, the last one is we have find the integral representing the area of the regions enclosed by x equal that, and x equal that, and then x equal that. So one of the general feelings that it gives me is that I'm gonna have to work on it just on the x direction, but let's graph it out and see how it works. So the first one, x equals square root of x minus y squared. So this one is when you have x equal square root 16 minus y squared. I absolutely have no idea how it looks like, but there was one thing you can try, and I would say try that when you square both of them, 19 minus y squared. Now it gives you an idea, is this a part of a circle? But you just have to figure out which side is it? Is it like this part, or is it this side, or is it this side, or is it the top part, or is it the lower part? Now it's because it's of x, it can only be like the two sides, the left or the right one. And here x is a square root, so it's a positive value, so it's going to be this part of a circle. So I'll draw it in another color just for the purpose. So this is 4, this is minus 4, so it is also 4. So this is the x equals square root of 60 minus y squared. Now that is one curve. If we look for another one, the second one, x equals 2y plus 4. Because this is going to be x. So x equal 2y plus 4. But if you're usually used to the fact that you will find you usually draw a straight line, because here you can see it's a straight line. If you used to draw a straight line with y with respect to x, you can also put it in the form of x over 2 minus 2. So x over 2, the slope is half. So at x equals 0, it's gonna equal negative 2. And when x equal to 2, it's gonna equal negative 1. Also, you can put in 4, and that's gonna equal 0. So this is the two line that pass through it. So this is x equal 2y plus 4. Now the last one is x equal a quarter of y plus half, and then the entire thing square. So clearly, one thing you can see is that when you have y equal to negative 2, then x equals to 0. So it also crosses this point. I'm going to draw it with another color. It also crosses this point. And when y equal to negative 2, so y equal negative 2, x equals 0. So 0, negative 2. And then when y is equal to also 1/4, so you're going to have half plus half is 1. So you're going to have 1 and then 1/4. No, actually, it's 2. 2. When you have y equal to 2, you have half plus half. So 1 and 2, 1 and 2. So that is if you do the same thing. So I would say if you have y equal, so you can have -1 and square as well, right? So the negative inside -1. So this one is -3/2. So -3/2 is going to give me, so you need y equal to -6 to get 1 again. So -4, and so this one is going to be -6. So it's cross these 2 points, right? It's just a general graph, so you can see the fact clearly, like the graph that is area enclosed by this curve. So this part, give me a second, I'll redraw that one. Okay. So the area that we're looking for right now is going to be the area enclosed by this curve, x equal to y plus 4, this one, x equal that amount. So there are actually 2 regions that we can do with that. Interesting. So this is -2, if that's what we're looking. So there should be some other bounding area, some other bounding area that need some other bounding conditions. So because that's what I'm saying, like there are 2 areas that you can have the like the enclosing. So there are 2 areas that we can do. So what we can find is that let me give more specifying area, or we can just ignore the thing in the middle. So let's just ignore this one. So now we have like these 2 curves. So just this one is just x equal 1/4 y plus half square. Now to find the intersections, find intersections. So you only need these 2 curves. So you're gonna take the entire area in red. So you're gonna have square root 16 minus y squared equal 1/4 of y plus half square. Now both of them is positive, so I'm gonna square both sides, and I'm gonna have 1/4 y plus half to the 4th. This is horrible to look at this. I actually think this is not a very great idea to do, but if we change what we're looking for, so everything in red is going to be deleted. Actually, let's not do the square one because it's too hard and it takes a lot of time to kind of like just finding the intersections, even though technically that's what you have to do. So I'm just gonna make life easier by just caring about the second part using an easier one. So I'm just gonna take the area between this and this. So this is the area that we're looking for. I would add in also I would use x equals 0. So the y-axis as well. So if we have this boundary, this boundary, this boundary, so this is the regions that we're looking for. So then we're gonna find what is the intersection. So the first intersection is at x equals 0, and the other one is at x equal to 4. One other thing you can do is just set the intersection with one equal to one another. X equal to that, and then you have another one is x equal to 2y plus 4. As I say, this one we already make it into the form, so 60 minus y squared square root equal to 2y plus 4. So if you square both of them and try to find what value of y that give you this, you have 4y squared plus 16 plus 16y. Therefore you have 5y squared plus 16y equal to 0. I wonder if I did something wrong here. So anyway, what you're gonna end up finding is that you're gonna find y equals 0 or y equal negative 16 over 5. And this one is not correct because we're bounded by y equals 0, by this negative 16 over 5. Negative 16 over 5 is all the way down here. So it's going to be the other intersections that after this part when you have this curve and then it's gonna cut the circle. So it's gonna be this way, but we already bounded by x equals 0. So we wouldn't go over there. So what we end up having is right now is going to be so we only take, so the two intersection is as y equals 0, x equal 4, and then y equal negative 2, x equal 0. So this is the intersections at 4, 0, and 0, negative 2. So now is where we're gonna find the area. So the area, as you can see it in here, it will be so much easier if you just take from in the y directions that this part minus this part from x equals 0 to x equals 4. So the area that we're looking for is from 0 to 4. The above curve is x over 2 minus 2 minus the below curve is in the form of y. That one is going to be square root of 16 minus x squared dx. Here you have x equals square root of 16 minus y squared, be that function. So if you square both of them and 16 minus x squared. Now, the thing is that you have to figure out is this plus or minus. Actually, it's going to be a minus because as you can see the fact that this part, y is negative. So y is negative, so it has to be negative of that curve. So this one, because it's minus of minus, is going to be a plus. So this is our integration on the dimension of x. But if you change to do it in the y direction, you can put it into two areas as well. In the x direction, you have 0 from negative 4 to negative 2 of y. So the above curve is going to be square root of 16 minus y squared minus 0. Square root of 16 minus y squared minus 0 dy plus from negative 2 to 0, the above curve and minus the below curve. So square root of 16 minus y squared minus 2y minus 4 dy. And this one is not hard either. Like this one, you also have to use like two techniques. First is regular integration, and the second one maybe like sub tricks up. And this one is also the same. You have to use tricks up and also tricks up here. So, but the question only asks us to set up the integral. So that is what we're gonna do. That is our final answer because this doesn't require much. You can maybe try to like simplify a little bit more depending on what your answer choices are. But this is kind of like the way we're gonna do it. And sorry for putting this one up. It's kind of like very it makes the problem way more complicated, and I don't think you're gonna be asked something that's difficult in the exam. So having said that, This is everything I have for today. Practice problem. Please do all the suggested problems on Canvas, and also try out maybe this additional one on in the section 5.1. So if you don't have any further questions, I'll end the sessions here, and I'll see you guys next week. Have a great weekend.